In this section, we're going to explore a couple things. One, we're going to look at sample size, namely how large does the sample need to be in order to um, conduct a survey or do a study in order to get the error that we want and make the estimates that we would like. And then we also want to look at confidence intervals just a little bit more and ask some broad stroke questions about them. All right, so let's look at sample size to start with. So the first thing we're going to look at is from section 9.1. So I broke it off of that original section and I'm putting it here instead. And it's estimating the sample size needed to estimate a population proportion. See that? Proportion? Let me highlight that. With a specified margin of error. Sorry, I didn't like that color. All right, so we're going to look at proportions, and I always get this question from students because they always say, oh, they only polled 1,000 people. 1,000 people is not that much when you think about the size of the whole country. And my answer to them is, no, actually, it's okay. I mean, it's okay that Gallup and CNN and whatever news organization you want to talk about, the Pew Research Foundation, things like that, they can poll sometimes, often, around 1,000 people, and it's totally okay. So why is that? Well, there's kind of a metaphor for this. When you're sick and you go to the doctor and they want to figure out what's wrong, they draw blood, right? But do they need to draw all the blood in your body in order to figure out what's wrong with you? Well, no, right? They don't need to do that at all, thank goodness. They need to draw a sample, a nice, random, unbiased sample, but a sample nonetheless. So all you need is a sample of a few vials of blood in order to know what's going on. Well, the same is true for your sample size, right? You don't need to poll everybody in America. You just need to have a good, nice, random vial, i.e. sample, of people. So then how big is a big enough vial? I mean, obviously they don't take like a thimbleful. They take a little bit more. So how do we know how much we need to take? That's what these formulas are going to help us with. These are going to be the formulas for finding the sample size needed to estimate a population proportion, P. So when they ask how many people, this is the kind of question that you want, or that is the kind of question that you want to use these formulas for. Now, you do not have to memorize these formulas because they are right on your note sheet. If I go to the inferential statistics sheet yet again, the confidence interval ones were up here, and if you scroll down, the sample size formulas are here, right here. So we're looking at these two right now for 9.1, which is a one sample proportion with a prior estimate and without a prior estimate. So here's the one with a prior estimate. Here's the one with no prior estimate. See the word no in there? I don't know why I have no a prior. I think that was originally not a prior estimate. So with no prior estimate. Okay, no prior estimates. I'm going to highlight it in blue, for example. There we go. And then prior estimate is going to be green. So you can see them. There, and I'm not going to highlight those words because it's just too big. So I'm just going to bold them for you. Now keep in mind, we want to round both of these formulas up to the nearest whole integer. You don't round them with regular rounding. They always round up. And the margin of error, E, must be a decimal for these two formulas. Now the rounding up part, I actually put right here. Always round up, no matter what, right there at the top. So it's right there in the neon green sheet you get to use on your exam. All right, so let's look at this. Suppose we want to know how many students we need to poll to find out whether statistics professors at JCC are awesome, right? So how many people, oh, technically we're just JC right now. How many people are we going to need to poll if we want, and then for all parts, for every part I'm about to show you, show the formula, show the substitution, show all the work. Okay, so we want to be 95% confidence with a 4% margin of error. So how many students will we need to poll? Well, since we have no prior estimate, we have to use the bottom formula. We don't have any previous study, for example. So we're going to have to use this formula right here, that n is equal to 0.25 times z alpha over 2 over the error squared. All right, good. Well, the 0.25 is pretty straightforward. Now, the error comes out of what they give us. So they're telling us that they want a 4% margin of error. See that right there? Right, so if they want within 4%, that would be your E. Your error is 4%, which is 0.04. And you have to use the decimal. It says right here, you must use the decimal. So that means that my denominator is going to be 0.04. Now all I need to do is figure out my z, and I'll be fine. Oh, but remember, we learned the z for 95% confidence, but in case you've forgotten how to do it, let me just remind you. Alpha would be 0.05, right? So that means that alpha over 2, there we go, alpha over 2 would be 0.025. So let me go back to the t-table real quickly. T-table right here. There's the chi-square. 0.025 is right here in the middle. And we want a z-score, so you go to the very, very, very bottom, and there's the z, 1.960. So this one's in our table, so we can just use the quick reference. So z alpha over 2 is equal to 1.960, right, from the table. All right, now that we know all those parts, we can use them in order to come up with our results. So we're going to take this and put 1.960 right here in the numerator. And from that point on, it's just a simple calculator issue, right? So you need to type in 0.25 times 1.960 over 0.04 all squared. So let's see here. I can actually type it all at once. 0.25 parentheses 1.96 divided by 0.04. There's my error. Close my parentheses. Square it. Don't forget to square right there. Lots of students do. And press enter. And you get 600.25. But we must round up. So we're going to have to make it 601. And that will be our answer. Just a little reminder, you must round up, no matter what. All right, so that's all well and good. And let's do it again now, but this time they want a 95% confidence still, but they only want a 3% margin of error. So same problem, but I'm changing my confidence, or excuse me, I'm changing my margin of error from 4% to 3%. So that means I'm going to be able to take a lot of what we have here and just paste it in down here. But the difference is that it's 3%, which is going to make 0.03. Since it's 95% confidence, this 1.96 part hasn't changed. So it's going to be 1.96 over 0.03 squared, and then you multiply it by 0.25. So let me grab the calculator. I'm going to teach you a little trick. All I want is that last thing I entered, so second, enter. And that brings back what I just had. And then I can go in here with my arrow and change it to 0.03. Enter. And I get 1067.111. Right? 0.1 repeating, I should say. Okay, so that means that it's about 1068. You must round up. All right, now what do we notice here? We went from a 4% margin of error to a 3% margin of error. So when we did that, when we lowered our margin of error, right, what happens to the sample size, right? So you lower your margin of error, then your sample size increased, right, by quite a bit. We went from 601 right here, so we needed 601, and now we need 1068. So there's an inverse relationship, and it has to do, it's because errors in the denominator. So let me type this up. All right, that's called an inverse relationship. Let me underline it and italicize it so you can see it, right? Between E, your error, and N, your sample size. So since E is in the denominator right here, let me show you. Since E is down here, then what happens is if it gets larger, if your error gets larger, then the overall fraction gets smaller. In other words, N gets smaller. And if E gets smaller, which is what we did, we made it turn into 0.03, then N becomes larger. There's an opposites relationship going on here. When E goes up, N goes down, and vice versa. It's because E is in the denominator. That's why this is happening. All right, now let's suppose we leave the 3% margin of error alone. So we're going to stick with that 3%. But now I want a 99% confidence level. Well, that's going to leave the error as 0.03, but something else is going to change on us, namely the 1.96. See, the alpha is now, if I have 99%, it's 0.01. And that means that this is 0.005, right, which is 0.01 divided by 2. Now I need to go grab the table. I want to go to the 0.005 column. Go to the very, very, very bottom. You can see it's 2.576. Or if you like, if you recall, we learned how to do this with inverse norm. So distribution, inverse norm, which is number 3, 0.005. Enter. This will give us the negative, but it doesn't really matter. There, see, 2.576. Okay, so let me go back to the problem. And that means my z right here is going to be 2.576. And I can say it's from inverse norm 0.005, comma 0, comma 1. Or if you like, you can say from the table. Either one, whichever way makes you happy. There we go, from the t-table. All right, so that's 0.03. This is n right here. All right, so instead of 1.96, I'm going to have 2.576. Now notice I'm increasing a number in the numerator. So it's going to be interesting to see what that does. So I'm going to say 0.25 parentheses 2.576 divided by 0.03, close parentheses, and square it. And then I get 1843.27. Okay, so 1843.27, which is 1844 because we must round up. And this was approximate here, so. And there we have it. So now, notice what happened here. We increased our confidence level this time. We went from a 95% and the one above, this one was 95, see it right there, to now a 99%. So what happens then? Well, because confidence affects your z. The bigger your confidence, the bigger your z-score is. Then that means that it's going to have a direct relationship. It's not going to have an inverse relationship like this one did. So this one had an inverse because error was in the denominator. But the confidence level is going to have a direct relationship with our sample size n. Okay, so I typed this up. So because confidence level affects z, and z is in the numerator, there's a direct relationship, not an inverse, but a direct relationship between your confidence level and n. In other words, if your confidence level goes up, then n goes up. And when your confidence level goes down, n goes down. Here I should say and instead of also here. And then I realized I should have said increases, not increased. And the same thing here. If your margin of error stays the same, so you leave it at 3% and you increase your confidence level, then your sample size is going to increase as well. All right, now last but not least for this portion, suppose we had the results of last year's poll about statistics professors at JC, and it was found that 67% of students think that they're awesome. Now, how many people would we need to question in order to be 99% confidence with a 3% margin of error? So if you'll notice right here, I'm using the same confidence level and margin of error as the last problem. Okay, but we have this prior estimate right here. See that 67%? That's from an old study. That's what prior means. Prior means in the past. So I'm going to get to use this top formula right here, the p hat 1 minus p hat. So let me type up that formula, 1 second. Okay, so I know that p hat is 0.67, 67%, that's where that comes from. And then I know that my error is still 0.03, no troubles there, that comes from the green portion. And then the 2.576 is just what we found up above, so that hasn't really changed, it's right there. And I'll just change it, we found it in inverse norm. So all I need to do is go type this in a calculator. So I say 0.67, parentheses, 1 minus 0.67, close parentheses, parentheses 2.576 divided by 0.03, all squared. And sure enough, I end up with 1630.19, which is about 1631. So you don't need as big a sample if you're working from an old study because your prior estimate helps out.